thanks to everyone that's able to make it to today's first ever live Tech Talk event. Today's Tech Talks can be focused on HAB monitoring and technologies to be able to make that more efficient. And it's going to start out with a presentation. It's going to last around 30 minutes or so. It's going to be given by our senior application scientist, Lawrence Yonan. And that being said, I'm going to pass the baton over to him. Take it away, Lawrence.
Thank you, Patrick. Thank you, Michaela. Hello to everyone who has joined us and welcome. I also want to say thank you for joining our first Tech Talk in what I hope to be a series of Tech Talks that Turner Designs will put out. And today's Tech Talk, to begin, is a lighthearted talk. I pretty much just we want to pass along some information that can help you who are interested in HAB monitoring make that effort a little easier. In our minds, a lot easier. And I'll go over some benefits of these new methods and technologies that we have that you can use for monitoring HABs. Talking about the overall steps that are involved in sampling. And I was going to share one of my experiences in water sampling, which can be fun at times and can also be a little dangerous, I guess we'll say. And back in grad school, I did this on a weekly basis. I went out to my sample sites, my sample stations, and collected water for taking back to the lab for extractive procedures and looking at extracted chlorophyll and other pigments as well. Well, there was this one day where I was in my little boat out there a mile offshore in Monterey Bay area, and I was in the water, reaching over the side of the boat, collecting water in my bottle, and like 8 orca fins 30 feet from me just breached the water. Scared the heck out of me, needless to say. So picked up my water bottle and hightailed it right back to shore. It's things like that that can be difficult at times to take a good sample. There are some dangerous areas. Maybe our sampling stations have to be defined in an area where it's easy to access, but it's not really worthwhile for us to sample that station. I would prefer to sample that station, which is a little more dangerous to get at. Or I need a bigger picture. So what I'll do is I will, spread out my sampling stations to collect water from many locations. Anyway, water sampling, pretty much going to your sample site. Let me get that next slide up. Going to your sample site and collecting a water, all you're trying to do is look at that little box I have in gray there, which has algae in that water sample. And that's your goal, is to quantify how much algae are in the water, or the abundance of algae in your water at your sampling site. So there are ways we can get around actually taking water out of the field and taking it back to the lab, because we're talking about factors that influence that algal abundance. You have factors like increased grazing rate, because you've now bottled the grazers in with the algae. You've got factors like temperature, time, transit. You have to take it from the field back to the lab. In certain cases, it can be a 3-hour trip, a 5-hour trip. Some cases are 5-minute trips. So that is one step. The second step into this extractive procedure method for looking at quantifying algae in water is the processing. Right now, I'm going to just stop and say, I'm going to put process in a box. We'll come back and discuss it. But that would be the second step to this whole protocol. The third one is you get your results. Your results are right there in quantified concentrations of algae, and you can use them for reporting or whatever that may be. So a very simple, when people talk about extractive procedures for looking at abundance of algae, you're looking at those 3 general steps: collect water, process, results. Well, let's dive a little deeper into the processing part of that. And when we do, it becomes painful. It absolutely was painful for me back when we didn't have these great tools these days to do this kind of work for us. And the steps involved in processing, and I'm going to start with the first one, a very simple one: obtain the materials. I ran around looking for materials that helped me complete this extractive procedure. And what I've listed there under number 1 for obtain materials is a portion of the list, of the full list that's required of all the materials for this procedure. I had to stop. I ran out of room on the slide. So you see at the bottom, and so on. So what I'm going to do right now is stop right there at that number 1 step, obtain materials. Because from this point on, it gets even more painful. One of the biggest factors disadvantages to doing extractive procedure is the wait time. After collecting your sample from your sample site and then you go back to the lab, you start running all these materials to extract that algae from water, the chlorophyll from algae. You have to wait for the extraction to occur. Typically, it's 24 hours. That's a typical time period set into all protocols. It may be less for some, two hours if you know you're dealing with green algae, but generally 24-hour wait time is what we used. And after 24 hours, you end up with 25 data points that you're reporting for all that work that went into this protocol, for all that pain that you experienced, which I did personally in this protocol. 25 data points for that one sampling event. Okay. So let me talk about why these extractive procedures are here and why people still use them. They were designed for instruments like this Model 10 fluorometer way long ago. Okay, and as we moved into the digital age, people continued using these procedures because they were set in stone pretty much. They are the almost baseline procedures that we use for looking at quantifying algae in our systems. But with advancement in tools, we have to advance our now protocols, now procedures for looking at these same types of parameters. Because the tools these days, they do a really good job. And I've circled on the screen there currently what the state of the tools has become. We went from this really big old dinosaur, hard to carry, tough, to a very small handheld fluorometer, which can be deployed and which can report to data logging integrated with almost anything now, CTDs, data loggers, telemetry. So these advancements allow us to now get into the field, and that's what we want to do, is deploy instruments into the field, not bring water back to our labs for instrument research. Here's a little sketch that I made just to kind of reiterate the point. There's an algal source that's depositing algae into a system. That system can be 5 miles long, 10 miles long. Let's say it's a pretty wide or long system there. And you'll see the gradient of algae that's set up. It goes from low on one end of it to high at the other end. If you were out there sampling this 5 mile long, let's call it a river or estuary, where would you do your sampling? Not knowing your gradient. You would have to sample multiple weeks, maybe months, to decide where your sampling points would be. And are they accessible? As I mentioned about water collection in the beginning. Can I design my sampling station so I can capture the structure that actually exists within the system? You know, it becomes a tedious effort. It's a little tough to do. I've experienced it firsthand with trying to define my sampling stations along an 11-mile long estuary. And I had 6 sampling points over 11 miles long. And I got I guess a decent picture of what those algae were doing along that estuary. However, it's only when I turned to in-situ fluorometry that I actually got the full picture. And what I mean by that is you take these small tools, you put them into your system at specific locations, and you leave them there. And they're recording continuously, and they're outputting data continuously in concentration estimates to data loggers, telemeter back to your computers while you're sitting in your office or in your lab, and you can see these data updated real time. This is really important for increasing your temporal and spatial resolution along big systems like this. They could be lakes, they could be estuaries, rivers. They're little to no maintenance these days. These tools are real easy to handle. They are quick integrations. A lot of them have self-maintenance, wiping capabilities, copper for anti-biofouling, other anti-fouling measures. So they can last for a long time when deployed. They're meant for long-term deployments, as a matter of fact. They're rugged instruments. They do not break down. They cannot be damaged most of the time. So this is the benefit of having in-situ fluorometers these days versus our traditional extractive procedures. Now I'll explain that in a little more detail as we go on. But these new age instruments can be now pre-calibrated. And we can put them into our systems for reading mixed algal populations and converting that response to concentration estimates. And this is easily done. And we could use our extractive procedures for this purpose. Now, extractive procedures, I'm not discounting them. They are good procedures to use. They're well written, well documented, well revised. But they don't need to be carried out on a daily basis for looking at algal abundance in water. It's too much work. Do the work up front for an instrument like an in-situ fluorometer, which you can then deploy and have that work done for you on a really fast, rapid timescale. So if you remember, I put up the table that we had of my 25 data points from my extracted chlorophyll procedures. And I'm going to plot those points here on the y-axis. It says in vitro estimates. Those are my extracted values. Now, for every one of those 25 samples that I have there, I have measured using an in vivo fluorometer, a fluorometer that I would put out into the field, one that I've calibrated. What this plot is telling me is that I can get pretty good chlorophyll estimates using my in vivo calibrated fluorometer. And I'm only overestimating by about 11%. But now, given all of the error that could exist in extractive procedures, that may be closer to a 1-to-1 ratio between in vivo estimate and in vitro estimates. So that's something that has to be analyzed more. But for the time being, my fluorometer was calibrated using a culture. I'm reading mixed algal populations. I'm getting only 11% overestimate in my in vivo readings. Imagine the kind of work that I could do if I were to take my algal population from my system and calibrate my fluorometer using extractive procedures to that sample. I would be a 1-to-1 right there. And I could, with confidence, put my in vivo fluorometer in my system, and then my concentration estimates would come back to me, and I could trust that those are as accurate as my extractive procedures. What this all leads to is better data resolution, guys. That's what we're talking about. Data resolved as quick as per second. Fluorometers these days are solid state. They don't have drift that we tend to associate with benchtop fluorometry. Now, those old fluorometers, I know for a fact, lamps faded, filters faded, they had moving parts, they had to be continually reset for sensitivity and recalibrated on maybe a monthly basis, I would say. And I'm sure some of you who are dealing with those fluorometers do this sort of work. These days, solid state fluorometers do not have moving parts. They run off of LEDs, glass filters. These things don't degrade. The other benefits to this is no missed events. If you take a look at what's on the screen right there, the green is showing you chlorophyll data over a month. If I were to tell you, let's go out to your sample sites and take samples, bottle samples for extractive procedures over a month, how many samples could you tell me you could take? I'll tell you what I did back when I was in school. I did 25 samples a week. That was a lot. I bumped it up to 50 samples a week, and that was my maximum. I'm a 1-2 person show back when I was doing my research. That equates to about 400 samples in a month. 200 samples in a month, 200 to 400. So what I'm showing on the green there is about 8,000 plus samples, 8,000 plus concentrations of chlorophyll being logged. I could pick out very small events there that I can't if I was doing bottle sampling, extractive procedures. I could correlate those data with depth. I could correlate them with temperature. I could correlate them with other pigment data or dissolved organics, or just different inflows that happen, or rain events, things like that. This helps me better understand my system versus my spot sampling, which I was doing, which gave me 200 to 400 samples in a month. And you're probably wondering, well, you know, how is it that you can get away with this given all the interferences? Because extractive procedures remove those interferences. True. That's true to a certain extent. Back in the old days with those benchtop fluorometers, we also had interferences. But what people did is use extractive procedures to remove those interferences, exactly what we just mentioned. Why did we have interferences? Because we used filters that look like this wide band pass excitation, wide band emission filter. These are old style filters. We have new age filters that have come onto the market, new technology for filters. We can now make them 10 nanometer bandpass. You see these very small peaks, excitation and emission here I'm pointing to. They're very narrow band, can pick out chlorophyll very accurately without any interference from other materials that are in the water. Because we can do this for chlorophyll and these filters can now be custom for these specific wavelengths, we can do this for other pigments that fluoresce. And two of the important ones that we're looking at these days are cyanobacterial phycobilins, like phycocyanin on the left there and phycoerythrin on the right. And what I've circled here on each graph is excitation emission spectra for those pigments. We can choose filters in a very careful way so we could pinpoint that pigment's fluorescence and pick out PC containing algae, PE containing algae, and distinguish or calculate or estimate the abundance of cyanobacteria within total phytoplankton populations. And we've done that already in a handheld version of it called the Cyanofluor, which is a great little tool for looking at cyanobacterial abundance in mixed phytoplankton populations. And really all this instrument does is very carefully look at the phycocyanin fluorescence and the chlorophyll fluorescence. And we can see by looking at PC to chlorophyll ratios how much cyanobacterial material is in that sample. And it clearly distinguishes, as you can see in the boxed orange here, in the orange bars, those are cyanobacteria. And the PC to chlorophyll signal is way above 1. Whereas if you're looking at non-PC containing algae, we are way below 1, we are near 0. To give you a better idea of how this happens in a ratio, I did a little experiment in lab just for the purpose of displaying this. What I start with here, so this on the x-axis, by the way, is just fluorescence response. The blue is fluorescence response of chlorophyll. The red is fluorescence response of phycocyanin. And I start with 2 milliliters of a non-PC containing alga, green algae. And you'll see the fluorescence response from PC is 0. So the PC to chlorophyll ratio would be closer to 0.01, closer to 0. As I stepwise add in my cyanobacteria into that same cuvette, I'm increasing the cyanobacterial population or abundance in that cuvette. Therefore, I'm increasing the phycocyanin content of that sample. This is mimicking cyanobacterial productivity. When cyanobacteria start to become productive, they are ramping up in numbers, increasing the phycocyanin of the sample, just like I'm doing in my cuvette here. At the end, what I've done is I've added almost 2 mils of cyanobacteria to 2 mils of green algae. I have a 50% abundance of cyanobacteria in my cuvette at this endpoint. My PC to chlorophyll ratio is represented as 0.51, 50% being cyanobacteria. This is a real easy thing to wrap our minds around. Just taking the PC response and the chlorophyll response and creating a ratio. And this is all done in vivo. We don't even have to look at extracted values of this. I'm gonna give you guys a little case study that my kids did. They're 7 and 9. And I took them out. We live right across the street from this lake. It's a man-made lake. And the lake actually is an overflow for this stream that runs by it. Is a canal, which at times when water's high, there needs to be a relief or else there's gonna be some kind of flooding that occurs. Well, this lake was created so the stream would flow into this high flow, would flow into the lake and be captured and then flow right back into the stream, kind of like a catch for the stream. Well, during low flow season, summertime, this end here at the bottom, South Basin, dries up. There's little flow going into the North Basin from the stream because it's really low water levels. What happens is you have the perfect recipe for breeding cyanobacteria. High temperatures, we're talking summer, high nutrients, because there's a lot of waterfowl there, ducks, geese, and stagnant water, water that's still, not moving. This was a perfect test bed. So I told my kids, you know what, let's go out there, grab a Cyanofluor. Let's see if you guys can do a quick experiment for me. They love this kind of stuff. So we went to 4 sampling stations that we chose along this basin. and one in the stream. We did a north basin, stream, south basin, and a bridge just to compare the differences there. And what we found is I collected the samples. I didn't want them to touch the water. They ran them in vivo. They took a cuvette, ran raw water. My collection, my extraction of the chlorophyll in those samples told me that the bridge, and I'll go back to it, the bridge area, which is right here, had the highest levels of chlorophyll. Therefore, to us, that would translate to the highest abundance of algae. My kids told a different story with the cyanoflora. They said, no, Dad, the South Basin has the highest amount of algae. They were right. The highest PC to chlorophyll ratios that were detected by the cyanoflora existed at the South Basin. And the South Basin is, again, I'll go back to it, right here. And that was simply from taking raw water and making a raw water read. I had a lot of pain processing my samples. I had materials I had to gather, I had a fluorometer I had to calibrate, and I had to make sure that my extractions were fully extracted and grinding those tubes because I expected cyanobacteria to be in the water column. Their experiment lasted an hour. Mine lasted a day and a half. They had a better answer than I did. Really simply, we can't just be tracking chlorophyll or looking at just chlorophyll signal. We can't also just be tracking phycocyanin, by the way. And I'll get to that in a little bit. The better way to understand cyano-HABs is to be tracking both and doing this ratioing. By doing that, what you're looking at is both streams, as you would be just monitoring both streams. But the ratio will give you productivity of those cyanobacteria in your mixed sample population. So what you see here in the top graph is a jump from about 5 microgram per liter to 15 microgram per liter. Some people may look at that and that may be cause for concern. They may say, you know what, cyanobacteria had a really high limit here, but really they're not. That could be just an effect of the total phytoplankton population increasing in that magnitude. Whereas if you're looking at the bottom graph now, the 5 to 15 jump, but the crossing of that total phytoplankton population is indicative of cyanobacterial production. Now we know PC is being produced at a higher rate in the water column. That's only due to cyanobacterial abundance increasing. We're headed for a HAB, is what the result would be there. We can use mitigation techniques at that point. We can stop it early. We don't have to get to these high HAB levels or levels where you see matting or you see this green soup. The other thing these PC to chlorophyll ratios are good for is for determining false positives. If you have your in-situ probe and there are turbulent conditions in the water, bubbles, that could cause false positives, pings in your probe. And here's a perfect example of that. This was a water state board that had set this up. And what they did is they set a limit of 20 ppb as given by the fluorometer that they were using, which is a phycocyanin fluorometer in situ. And they said if this signal goes above 20 ppb, there's cause for concern. There's a high probability we have health effects, negative health effects that can come from that. Well, you see at most of their sites here on the x-axis, it's well above 20 ppb. It's actually well above 100 ppb. So if above 20 is health effect, above 100 is shut down completely. That wasn't the case. They were using also a cyanofluor to do this type of testing. So they were able to show that just because levels in the probe's response hit well over 100 ppb, the PC to chlorophyll ratio was well below limits that indicate a high amount of cyanobacteria. That was primarily due to turbulent waters, is what it boiled down to. In this way, we can avoid these false positives. We can get a better idea of what our system is telling us by looking at ratios. With these ratios, we can then develop tools like the PhytoFind, which is an algal classification tool, and have in situ ratioing rather than handheld, which is what we are currently doing, or what most people are currently doing, is collecting a sample, putting it in a handheld and having a read. Although that takes a 15-second, only 15 seconds, still a lot quicker than extractive procedures, we can have this tool that can help us with monitoring or surveying systems as a deployed fixed position, or what we show here is it deployed or towed behind our boat as we moved up this 11-mile long estuary. And we could see these changes occurring in our data, which is very exciting to see. And these changes that you see on the screen were actually expected because I have researched this estuary quite a bit. That was part of my master's work. So I know what exists there. So it was very nice to see that the PhytoFind was picking this up. What I'm showing on the screen here is how that PhytoFind operates. So what's going on is you'll see extraction-based percentages calculated in the closed dots and those traces. For PE containing algae in red, PC containing algae in orange, and all other algae in green. And in the open circles, you'll see those are in vivo PhytoFind-based percentages. Pretty much it's what I'm showing you is what is the percentage of that group at that time. And how does a PhytoFind calculate that percentage? It does a very good job of actually tracking those extractive percentages. So the PhytoFind is a nice tool for doing these kinds of surveys, monitoring. It can be an accurate tool for giving you accurate information about the abundance of those groups in your system. And it can help with profiling, of course, which is oftentimes hard to sample from with respect to grab water or grab samples. We used to use Niskin bottles, and there were these big bottles that you would drop to depth, cap them, and then collect the water. And that's only at a depth. And then we would do it again at a different depth. Well, and again, you're missing the resolution there. You need better resolved data throughout that water column. So we could use tools like the PhytoFind to help give us those better data. Ultimately, what our goal is to prevent HABs, to better understand HAB dynamics in our systems, to better understand what algae are doing, our algal abundance, how they're changing over time. So the need is better data resolution. The need is accurate algal abundance estimates using in-situ tools and rugged tools that can last. And I think we're at that age where we need to start thinking more about let's get into the field than let's take the field back to the lab.